Hi, everyone. Thanks for coming to our chat with the Biostat event today. Associate Scientist and Associate Director from the Johns Hopkins Biostatistics Center. Besides my other statistical duties, I'm actually one of the biostatistical consultant with ICTR since 2009. So it has been quite a long time for me with ICTR. So it's really great opportunity for me to chat with you about sample size calculation today, which is a very important topic we come across all the time in grant application. So for today's chat, I would like to give you a very high-level overview about the key concepts related to sample size calculation. I will expand on some of the topics that often cause confusion. After that, I would like to go over a few examples using a readily available sample size calculation software so that you can do some sample size calculation if you need to in the future. So for today's chat, it's really just to give you the opportunity to understand the importance and the relationship among sample size, power, and effect size in a study design. This is actually a huge topic. If you want to know all the details, we probably need a whole year's course to go over every technical details. But today, we just want to know the importance and some basic information for them. And then after this, I want you to know how to navigate through the parameters and how to gather information for those parameters in a simple sample size calculation. And I would also for you to walk away with the knowledge when you should consult a statistical consultant rather than carrying out the calculation yourself. Next page, thank you. I would like to start a discussion with the question, what type of study should have sample size justification? This is actually a very straightforward answer. Almost all quantitative studies can be subjected to a sample size justification, with one small exception, that is for some early exploratory studies, which we oftentimes call pilot study. The reason being, for this kind of studies, we don't have prior information available to base upon our sample size calculation on. Actually, in that sense, that's why this kind of study can be quite valuable because they provide sample size calculation information for future studies. Okay, so now let's talk about when should sample size justification be performed. In this diagram, you will see some terminologies. There will be that you have seen and written about quite often in a grant proposal. So sample size justification should happen after you have made a decision about research aims, hypothesis, study design, and the statistical methods. The order should not be reversed. If there's any change to those previous steps, the sample size justification needs to be carried out again. So this leads us to the fact that sample size justification really depends on your study goal, whether it's a comparative study or it's a study for estimating a parameter, for example, like a disease prevalence. And also the study hypothesis is directly related to the hypothesis you will be using in the sample size calculation. Then the study design gives the information about how many, about information such as how many treatment groups there are, how many interventions there are, and how those interventions will be implemented. Then as well as the study outcomes, whether it's a continuous outcome or it's a discrete categorical study outcome, they will decide what kind of statistical methods you will use, and then therefore it will be used in sample size calculation. Generally speaking, there are two sample size approaches. One is to calculate the desired precision for an estimate. That is the confidence interval. So from the study, we would know what the mean would mostly likely be for the population. This is one type of approach. The other approach is more common than this desired precision for estimate, which is comparison between groups. So it involves the statistical hypothesis testing and having sufficient statistical power to reject an incorrect null hypothesis. On this slide, you will see a list of parameters that goes into a sample size calculation. So there are detectable difference, effect size, sample size, alpha, and the power. So we will go over them one by one in the later slides. So to introduce this sample size calculation, I would like to start with a quarter room trial analogy, because this is really abstract ideas or concepts that oftentimes for students in statistics can take a while to understand. So in a typical courtroom, if you are familiar with, usually we assume the defendant is not guilty, which is for the time being accepted. We can call this a null hypothesis. We treat it as right now what the true state is. Then the prosecutor would be trying to prove that alternative hypothesis is true, which is about the defendant is guilty. So they hope to support this statement. As we know, the hypothesis of innocence is only rejected when an error is very unlikely, because no one wants to convict an innocent person. This type of error of convicting an innocent person is called the error of the first kind, and usually is controlled to be really rare. And then as a consequence of this asymmetric behavior, the error of the other kind is more common, which is acquitting a person when that person actually committed the crime. We call it a type 2 error. And then the power is conviction when the criminal is truly guilty, which is 1 minus beta. So if we think about this kind of setting in a research, we see a 2x2 table shown here. So this 2x2 table shows us the result of comparing the decision made from a statistical test as comparing to the true state for treatment benefit. As we can see, there are 4 outcomes. So we either correctly conclude there's treatment effect when there actually is, or we conclude there's no effect when actually there's no treatment effect. But then there are two types of error can occur. The first one is called false positives, when we say there's a treatment effect, but in actuality, there's no treatment. So we call this a type 1 error or alpha. This is the chance of finding, so we hope the chance of finding such error would be occur only on less than alpha % of the occasions. And then the other error is the false negatives, which is when we claim there's no treatment effect when actually there is. So this is beta. So we want the power is when we if a difference truly exists between the intervention, then we find it on 1 minus beta % of the occasions which is the power of this study. If you want to see this, all the parameters in a visual presentation, I'm showing you here the how those parameters fit in a statistical testing. So here you see two distributions. The blue curve is the sampling distribution under the null hypothesis, which means there's no effect for the treatment. And then on the right, you will see a red curve, which is the sampling distribution under the alternative hypothesis. So the distance between the two distributions is the effect size we would want to detect in a sample size calculation. And then in the red shaded area under the blue curve is the type 1 error, where we would reject the null hypothesis that there's no treatment when no treatment effect, when actually there's no treatment effect. And then there's a type 2 error, which is the beta, which is the blue shaded area under the red distribution curve. This area shows you when we actually, this is the false negatives, when actually there is treatment effect, but we claim there's no treatment effect. And then for the rest of the area under this red curve, which is 1 minus beta, is the power for the study. Oh, one thing sorry, Stephanie. One thing I forgot to mention in this curve is that the black line in the middle, that is the test statistics. So when we do the sample size calculation, if we calculate a test statistic greater than this black curve here, then we would reject the null hypothesis. And if the test statistics is smaller than this black line here, then we would fail to reject the null hypothesis. So this is just an illustration. So in actuality, the curve could be either on the right or on the left of this blue curve. So for this detectable differences, this is really related to the alternative hypothesis. So in a null hypothesis, we claim there's no difference, but then in alternative, we specify a difference that we want to detect. One thing I want to point out, this is really a researcher's decision based on the level of study, is whether it's a pilot study or subsequent research. So for pilot study, usually we would look at a larger detected difference, but in subsequent research, we probably want to look at a smaller detected difference. And then this also depending on the available resources for sample size. If we can afford a larger sample size, we may be able to detect a smaller difference. So the researcher usually gathers this information from their previous work or the literature on similar studies. If there's no information about this parameter, then we look at the effect size, which tells us the relative measure of difference. So this leads us to the effect size. This actually is a very confusing term because we use this term quite often without knowing that there's so many varieties of effect sizes. Just based on some rough estimate, there are probably more than 70% varieties for effect sizes. But just to summarize the two families of the effect size, one is called a D family, which is the difference between groups. And then there's an R family, which is the association between measures. If needed, we can convert between this R family and D family effect sizes. So here I'm giving you some examples about D effect sizes. For dichotomous outcomes, Some of the examples are the difference in probabilities, risk ratios or relative risk, and odds ratios. And then for continuous outcomes, using two groups as example, this D effect size is the difference between two means in standard deviation units. Please note that the standard deviation option actually can vary, depends on the situation. If the standard deviation are roughly the same between groups, then we use the pooled standard deviation to calculate the effect size. But if the standard deviations are not homogeneous between the groups, we can use the controls standard deviation. This is not affected by treatment. Those two situations are for equal group size allocation. In some cases, we may not have this equal groups size allocation. One group may have more sample size than the other. In that case, we can use this weighted standard deviation relative to the group sample sizes. So that's about the D effect size. Here is the R effect size. I know I listed a lot of terms here. You may be familiar with this Pearson's R, which is a correlation coefficient to measure the linear relationship between measures. There are also non-parametric correlation coefficient, for example, Spears, Rowe, Kendall's, Tau. So they measure the monotonic relationship between measures. And then another R effect size is another type is the proportional variance that you're very familiar with, is the R square or the adjusted R square in a regression. There could also be, like in a ANOVA setting, similar to the R square in multiple regression, there's the eta square, which look at a percent of variance based on group differences. And then another type for R effect size is the Cohen's F or F square. It's an incremental effect of adding predictors to basic models. I know this probably is not like the most common terms you would see. I'm just listing it here for your future reference. So when you come across those terms, you know what type of effect size this is. So here, I would like to summarize the relationships among the four parameters. So for the same sample size and alpha, when the effect size goes up, the power goes up. And then for the same effect size and alpha, when the sample size goes up, the power goes up. And then for the same sample size and effect size, when alpha goes down, then the power goes down. And then for same sample size and power, when the effect size goes up, the alpha goes down. Please know that the alpha doesn't rely on any of the other parameters. And in sample size calculation, we usually set alpha at either 0.01 or 0.05. And then the beta or power, which it relies on the other three parameters, sample size, type 1 error, and effect size. And this is really related to a specific alternative hypothesis. So now we know that statistical power is the probability of rejecting the null hypothesis if in fact the null hypothesis is false. So to improve power, to increase power, there are multiple ways we usually do in a calculation. The first one, of course, is to increase the number of samples. So the more we know, the more samples we have, then the more power we have in that study. And then the other one is to reduce the variability of the outcome, because this is related to the effect size. When the variability goes down, then the effect size would go up. And then we would achieve more power with that larger effect size. Then the third one is to increase the effect size and the detectable difference. Usually, the larger the difference or effect size, will try to detect the higher power we would have. When we decide on the effect size and the detectable difference, there are two things for you to keep in mind. One is we need to think about whether this difference is clinically important or not. For example, if we are carrying out a study about local anesthesia, we want to look at the reduction in the onset time. Should we be choosing the 1 minute or somewhere between 1 to 10 minutes as the detectable difference? We probably would think about somewhere between 1 to 10 minutes, because less than 1 minute is not really that clinically important. But at the same time, we have to think about whether this difference is clinically feasible. If it's something already being reduced to can't be any lower, then 1 to 10 minutes may not be a realistic goal. Then we have to go by a smaller detectable difference. Then the last one is we can adjust the statistical significance level, which is alpha. But there's really not much flexibility in change this parameter. Usually we would have to go by 0.05 or 0.01. So we don't really recommend making this significance level higher. So there are some other factors that can affect power. As we mentioned, can be a measurement error. So for your outcome, if there are more measurement error, means a higher variability for your outcome, that would decrease your effect size and therefore reduce your power. And then in some research, you may have subgroup analysis. If you want to see an effect for that subgroup analysis, you really have to estimate the smallest subgroup size, so you will be able to detect the effect you intend to detect in that subgroup analysis. And then as more subgroup analysis involves in that study, we come into the territory of multiple comparisons. So we have to adjust the alpha level accordingly to avoid this type 1 error. And then in multiple regression analysis, if we look at more effects, then we have to do more. That also comes. That's also similar to the subgroup analysis, because we have to look at each individual effects and then do more testing for each one of them. And then the alpha level should be adjusted accordingly as well. And then for some studies, there could be correlated measurements or clustered observations. For example, the patients within the same clinic may have some correlation in their outcomes. Therefore, we can treat them as independent individuals from each other. And this would affect your effect size. And then we have to factor in this design effect in your study. So those are the other factors that can affect your power you have to think about if this happens in your study. So to choose the right power level, it is really a fine balance. For underpowered study, if we can't reject the null hypothesis while wasting the resources for carrying out the study, this can also misdirect future studies if these results are not statistically significant, because people may wrongly make the incorrect decision or judgment that this treatment is not effective because of your study, but in reality, it's just your study was underpowered and didn't show an effect that was actually there. And if this study subject individuals to inferior treatment, and then this can be unethical. And then for overpowered study, we know that it comes at the cost of wasting resources and also pick up some essentially trivial results that can be meaningless to detect. And also the cost of collecting all those data is outweighing the benefits of having this many subjects in your study. So choosing the power level is really a balance between those risks of making the type 1 and type 2 error. The power of 0.8, we use it more often, like as absolute these days. It's really due to Jacob Cohen. So we usually use 0.8 and 0.9 just to see what sample size you would need to achieve this kind of power that we set as like a rule of thumb nowadays. So generally speaking, the type 1 error is considered worse. So we can, and if we can tolerate this 5% alpha, generally we can tolerate the 20% beta. And I oftentimes come across this question that, does statistical test affect power? The answer is yes, because this is really related to your study outcomes. So if your study outcome if you're going to use a parametric statistical test, usually this test would provide higher power than a non-parametric test. And also, whether your test is going to be a one-tailed test or two-tailed test. A one-tailed test usually gives you higher power than a two-tailed test. Also, for continuous outcomes, it will provide higher power than a nominal or an ordinal outcomes. But this is really depending on your study design and the statistical analysis. Therefore, when you design your outcome, it'd be helpful to think about whether you should choose a continuous outcome or a nominal outcome, or whether you want to use a parametric test or non-parametric test. For the one-tailed or two-tailed statistical test, it is used more often than the one-tailed. But if you know for sure that some treatment would be better than the old treatment, then maybe in that instance, the one-tailed is a reasonable choice for a statistical test. So to calculate sample size, here are the steps. The first one is to specify the hypothesis. In the alternative hypothesis, we need to define what is the clinically meaningful difference or a change. And then we need to find out the variability of the measure. What is the population variance that we can use as a variability in the calculation? And then for the significance level type 1 error and the level of statistical power or type 2 error, we set them as, for example, 0.05 versus a 80% power. And then there are some other considerations. For example, in some study, we may know there's a maximum sample size given the available resources to that study. And then we probably want to calculate what is the maximum achievable power given that maximum sample size. So for all those assumptions, if any of them changes, then we have to go through several iterations of sample size calculation. Now I want to give you, I want to go over a few examples so we can review those concepts. I know probably went over those concepts pretty quickly. So hopefully in those examples, you will have another opportunity to relate to what we just discussed and think about those parameters used in the sample size calculation. So in this example, this is a very typical sample size calculation problem for group difference for proportion outcomes. So here we have a study about treatment for cold. So we know that, so in this one, we assume there are about 50% of patients recover from cold within 48 hours. Then with this new cold treatment, this recovery rate may increase to 70%. We will use the usual alpha of 5% and a power of 90%. That is, if the drug is effective, we want a 90% chance of showing that it does indeed work. So how many patients do we need to achieve this 90% power? So for this question, the null hypothesis is that the recovery rate from cold within 48 hours is the same between the old and a new treatment. And then the type 1 error set at 5% and type 2 error set at 10%, which is equivalent to 90% power. So what is the clinically important difference here? As we can see from the description, we're looking at a 20 percentage point better recovery rate in a new treatment group as comparing to the old treatment. So here I'm showing you the Stata output, just in case some of you they're using Stata, you can follow this example in the future. So here I used the power to proportion syntax, where I input the assumptions about the proportions. So the P1 is 0.5 here, which is for the null hypothesis, that 50% recovery rate. And then the P2 is 0.7, which is the alternative hypothesis, which is about the new recovery rate for the new treatment. And then we want to achieve a 0.9 power. So I use a P parenthesis 0.9 in the command here. I don't know whether you see it's the first line here. And then what's under this is the output from Stata. As we can see that it listed all the study parameters. And then based on this those study parameters, the estimated sample sizes is 124 per group, and the total sample size 248. So that's the sample size calculation results for this example. So here, this is the G-Power software I mentioned earlier. So this is really nice free power calculation software where you can download no matter you're using Mac or you're using PC. So here I'm using the statistical test for proportions, difference between two independent proportions. And here we want to compute the required sample size given alpha, power, and effect size. So as you can see at the bottom left corner, there's a section for input parameters. So we specify this as a two-tailed test. And then we have the proportion P2 as 0.7 and the proportion P1 as 0.5. And we put in alpha and power here. And the allocation ratio is 1 because we have the same group allocation for the two groups. So once you set those input parameters, you click the calculate at the bottom right corner there. Then those output parameters will show up on the right side of the panel. So as you can see, the calculated critical Z value is 1.96, and then the group sample size is 124 for each group, and then total sample size is 248. And we achieved the actual power of 0.9. So this is similar to, this is the same as what we just saw in the Stata output. So for this sample size calculation, a summary statement would be group sample sizes 124 in the old treatment group and 124 in the new treatment group achieve 90% power to detect the difference between the group proportions of 0.2. The proportion in the new treatment group is assumed to be 0.5, same as the old treatment group under the null hypothesis. But then this proportion is 0.7 under the alternative hypothesis. The test statistic used here is the two-sided two-sample proportions test, and the significance level of test was targeted at 0.05. So I'm providing the statements here that actually you can, if you have similar sample size calculation, you can include this statement in your grant proposal. So this statement includes all the key parameters and what assumptions you made in the sample size calculation. So now this is another example using group difference for proportions outcome. So in this study, it compares the acute respiratory distress syndrome mortality rates between the titration ventilator setting using the stress index and the low tidal volume setting. And then the observed mortality rate in the low volume setting group is around 40%. So this is all the information we have for this sample size calculation. Then for the sample size calculation, what are the assumptions? So the null hypothesis is that the ARDS mortality rate is the same between the two settings. And then we have the normal type 1 and type 2 errors set here. So what's different from last example is here we don't really have a set value for the minimal clinically important difference. So the researcher has to look at a range, but then pick a minimum for this calculation. So for example, for this research, a 10 to 20 percentage points better mortality rate in the titration setting group compared to the low volume setting group is a reasonable assumption about the detectable difference. So based on those assumptions, we open GPower, we input all the relevant parameters here. So instead of the previous window, what I'm showing here is a plot window in GPower, which is also a very nice feature for this free software. As you can see, I'm plotting the total sample size as a function of the proportion for the second group, P2. So here I'm changing the P2 from 0.1 to 0.3 in the steps of 0.05. As you can see here, let's say the proportion in group 1 is 40%, P1 equal to 0.4. Then if we assume the detectable difference is 0.1 for the second group. So basically looking at a 0.3 difference between mortality rate for the two groups. And then to detect that difference, we will need a total sample size of 63. However, if we assume there's a smaller detectable difference where the mortality rate for the second group is 0.3. So looking at a difference of 0.1 in mortality rate between the two groups, then we would need 712 total samples to detect this difference with a 80% power. So as you can see, this is a really nice curve and a visual presentation to show you how sample size changes as we change the detectable difference between the two groups. So in addition to the plot, sometimes we would prepare a total sample size table so you can which record the information about how sample size changes if we change the assumptions for the parameters. here, in addition to the difference in proportions, I also included another assumption about the controls proportion. So here, let's assume the mortality rate is 30% in the controls. And then when we have that assumption, how the sample size changes for different assumptions about the difference in proportions. I just saw a question about where to download the G-Power. I included the link at the reference page, for the talk, so you will be able to see the link there. And now let's go over an example for continuous outcomes. So here I'm looking at experiment that's designed to compare the means of 4 treatment groups with a significance level of either 0.01 or 0.05. And then the previous study has shown that the standard deviation within a group is 18. And then the treatment group means are 40, 10, 10, and 10, represent the clinically important treatment differences. Then the researcher wants to know what the power will be for different group sample sizes between 2 and 14. Then the sample sizes will be equal across all the groups, so equal group allocations. So for this calculation, the null hypothesis is that the means of the 4 treatment groups are the same. And then we set the type 1 error at 1 and 5%. And then we're looking at a 20% type 2 error. The clinically important difference here are the group means, which is 40, 10, 10, and 10. And then the variability for the clinically important difference is the within group standard deviation 18. So those are the parameters will go into the sample size calculation. So once we have the information, we use G-Power. Here we are using a F-test for ANOVA with fixed effects omnibus one-way statistical test. So in the input parameter, you'll see that you're asked to input the effect size F. You'll be asking, what should be the effect size be? So what's nice about G-Power, it actually helps you determine if you have the mean and variability information. So if you click on that determine button, a window like you see on the right will show up. So here you select the procedure is the effect size for means. You enter the number of groups, and then the standard deviation within each group is 18. You put 18 there, and then in that table you input the means for each group and the n's for the group. So the total sample size is 20, and then you click calculate. Then the effect size F 0.72 will be calculated for you by G-Power. After that, you click calculate and transfer to the main window. This value will be brought to the input parameter section. So you don't even need to type it in yourself. So once you input all the parameters there, you click calculate, then the output parameters section will show you with the sample size, the power achieved would be 0.66. So because the researcher wants to know how the power changes as the sample sizes change, the plot comes really handy in this instance. So we plot the power as a function of the as a function of the total sample size. So we change the total sample size from 8 to 58 in steps of 8 here. So as you can see, the power changed from 0.175 to 0.996 as we change the sample sizes. So here, what you see actually is an output from another sample size calculation software called PASS. I don't expect you to have this sample size calculation software. It's quite expensive, but it has many features for more complicated sample size calculation. But I'm presenting the output here because I think it's a really nice report of all the important information you used in the sample size calculation, and it provides the report, the definitions for each parameter, and also includes a summary statement. So if you have any future sample size calculation like this, you can definitely use this as a template for reporting your calculation results. The information is exactly the same as what you saw from GPower. Oh, thank you, Stephanie. All right, so now let's, let me see. So I'm going to go a little bit faster for this example as we're kind of running out of time. So this one is a sample size calculation based on precision. So this researcher is planning a study to estimate the mean sleep duration per night in deep stages for sleep among Alzheimer's patients. So how many patients should she randomly sample to estimate the mean within a margin of error of 2 minutes? It is known from the literature that the standard deviation of deep sleep in this patient population is 15 minutes. So this is the information we have for the sample size calculation. So for sample size based on precision, so we need to select a level of statistical significance or the confidence intervals. So we know the 95% confidence interval for population mean is the sample mean plus or minus the standard error of sample mean times the z of 0.05 divided by 2. And then this highlighted component here is what we call margin of error. And then we know that for sample mean, it is equals to standard deviation divided by the square root of the sample size, and then the margin of error equal to the standard deviation divided by square root of n times the z of 0.05 divided by 2. I hope you know this is just some basic mathematical operations. And then after this, we can see that n equals to this formula here, and we plug in all the values we know, then we calculated n should be 216. So this one means a sample size of 216 participants produces a margin of error of 2 minutes for the 95% confidence interval for the estimated mean sleep durations per night in deeper stages of sleep among Alzheimer's patients, assuming a standard deviation of 15 minutes for this mean. So those are the examples. They are very simple calculations, but in research, we know that definitely more complicated sample size calculations, and usually more complex designs require more complex calculations. Some examples are like longitudinal studies, crossover studies, and or the correlation of outcomes. For those more complicated designs, we can use those simple calculation I just showed you, and GPower doesn't have the capability to handle this kind of calculation. So if you come across this kind, please consult a statistical consultant. And sometimes the simulations are even required for even more complex sample size calculations. So I would like to point out that some of the common statistical problems we saw in a proposal is that the sample size justification is absent or insufficiently justified. Oftentimes, actually, I also see that people carry out sample size calculation, but they didn't provide any information about the assumptions for those parameters. And also, another problem is the lack of statistical analysis plan for the aims, including secondary aims, or the inappropriate statistical analysis methods being specified in the proposal. Those issues actually can doom a proposal and are very likely to happen when the statisticians are not involved in the proposal preparation. So if you are unsure about any of those statistical components when you prepare your proposal, please don't hesitate to involve a statistician. So here are the references for some of the contents I showed here. I know it's a very quick introduction, and probably I didn't go into too much detail for the information you need, but hopefully the reference can provide some information. So this is the download link for G-Power, and there's some books about power and sample size calculation. And Stephanie, if you can go to the next page. This is a really nice introduction paper about power and sample size estimation. So if you are interested, I would strongly recommend you to read this paper carefully, and probably you are, along with what we saw went over here, you'll have a better understanding about sample size calculation. And lastly, I would like to acknowledge my colleagues who helped me with the slides, provided the examples that we saw here.